Greetings, calculus students. This lesson will be part 1 of a 2-part introductory series on a concept known as integration. Now, we will explore 2 different scenarios to introduce this concept, which will be explained later in more detail. Now, integration opens the door to an entire branch of calculus, which is introduced at the end of this course and is heavily explored in Calculus 2. Now, scenario 1. The velocity of an accelerating runner at various times is shown below. Time is measured in seconds, and velocity is measured in feet per second. Notice our time intervals from 0 to 2, 2 to 4, and 4 to 6 represent consistent changes in time. We can say, therefore, delta t is a constant 2 seconds. Now, plot the data below and find both an upper and lower estimate for the total distance the runner traveled in the first 6 seconds. Now, we're going to wind up doing 2 different graphs to illustrate 2 different concepts. But in both cases, the horizontal axis would be time, and the vertical axis in each case would be velocity, measured in feet per second. When time is 0, velocity was 4, giving us these 2 points. At time 2, velocity is 4.4. Time 4, velocity is 5.6. And at time 6, the velocity is 7.6. We will proceed with finding a lower estimate for the total distance the runner traveled. There are 3 different time intervals here, from 0 to 2 seconds, 2 to 4 seconds, and 4 to 6 seconds. For each time interval, we're going to assume the velocity was constant. So if I look at the first time interval, we only have 2 points of data, but we will assume that over this time interval, the velocity was the lower of the 2 options. So we'll assume 4 feet per second on the first time interval. On the next time interval, the lower of the 2 velocities is 4.4. And on the final time interval, the lower of the 2 velocities is 5.6. Now we know that if you are traveling for 2 seconds and you're assuming a constant speed of 4 feet per second, then you would simply multiply 2 times 4 and get 8 feet traveled. I'll characterize that as change in position. It'll be 4 times 2 equals 8 feet. The units of our time interval would be seconds. Velocity was feet per second, so that 4 is feet per second, this 2 is seconds, and this 8 is feet. Now this will be an underestimate because in reality, during the first 2 seconds, the runner's speed was increasing. For the next time interval, we do 4.4 times 2, and that gives me 8.8 feet. And on the third time interval, we do 2 times 5.6 to get a change in position of 11.2. So add these 3 numbers up, and we get 28 feet is an underestimate or lower estimate of the distance gained for time between 0 and 6 seconds. So in other words, in the first 6 seconds. Now visually what we've done, for this first time interval, of these 2 options, we assumed that the lower option was a constant speed over that entire time interval. We assumed the velocity did not change in the first 2 seconds. The height was 4 feet per second, and the width is our delta t of 2 seconds. And when I multiply 2 seconds and 4 feet per second, I get 8, which can be represented by the area of this rectangle. Just like you would multiply length and width to get area, you can multiply velocity and time to get an area of 8, but whose units are not traditional units of area. This area is representing a distance. So this begins the idea that we're using area to represent something that's not area, which we do in mathematics all the time. For example, using 2 different lengths to represent perhaps 2 different monetary values, where we use length to represent something that's not length. In that same sense, we're using area to represent something that's not area. Now for the second time interval, our 2 speeds to consider were these 2, and we assumed the lower of the 2 was constant across the entire time interval. So when you multiply that constant speed times the delta t of 2, once again you get an area. That area is 8.8, but whose unit is feet. And then on the third time interval, we had 2 different speeds to consider. We assumed the lower one was constant over that time interval, and we multiplied that constant velocity times 2 seconds, and we got a third area of 11.2, but whose unit is feet. Now we'll do an upper estimate. We'll use the same time intervals. We'll assume a constant velocity for each time interval, and then calculate the change in position based on that assumed constant velocity. This time, for each time interval, I'll pick the larger of the 2 options for speed. So for the first time interval, we will choose 4.4 as the assumed speed, and multiply by 2 seconds, and we get 8.8 feet. For the second time interval, we will assume the 5.6 was a constant speed, and multiply by 2 seconds, and we get 11.2 feet. And for the final time interval, we will assume 7.6 was the constant speed, times 2 seconds, and we get 15.2. Graphically, for the first time interval, we looked at the 2 speeds, one at the left, one at the right, and we assumed the greater one, which is the one on the right, and we retroactively assumed it was the constant speed for that whole first time interval. And multiplying that velocity times the 2 seconds, we get 8.8 as the area, but measured in feet. Second time interval, we assumed the right velocity, because it was greater, was the constant velocity for that time interval. And calculating this area, we got 11.2 feet. And for the final time interval, our two options for velocity were these. I'm assuming the one on the right, which is the greater one, to be a constant velocity over the interval. And this area was 15.2, also measured in feet. So adding up these areas, we get 35.2 feet as the approximate distance gained during the first 6 seconds. Here's our lower estimate or underestimate, and then our upper estimate or overestimate. And the reality is that the distance gained by the runner is likely somewhere between these two values. So often a strategy is now to average them to have a better approximation. But there are other ways to improve accuracy, especially if you have access to more data. Let's go to the next page. So we are still exploring the exact same scenario. Now the function that models the velocity of the runner is v of t equals 0.1 t squared plus 4. Fill in the table below, plot the data, and find an upper and lower estimate for the total distance the runner traveled in the first 6 seconds, but this time using 1 second intervals. Express each calculation in summation notation. We're going to plug in these 6 choices of time. Notice the gap from time to time is consistent. Our delta t is a 1 second. Furthermore, I'm going to say that our first time in our list, I will refer to as t sub 0, and then t sub 1, t sub 2, etc. Now it's just a coincidence that in this case, the subscript and the value of time match. If I change these 6 times to different numbers, I would still refer to them using this notation, t0 through t6. Now we plug these times into our velocity function. When t is 0, we're going to get 4. When t is 1, we'll get 4.1. When t is 2, we get t squared is 4, times 0.1 is 0.4, add 4 is 4.4. 3 squared is 9, times 0.1, add 4 is 4.9. 4 squared is 16, times 0.1 is 1.6, add 4 is 5.6. 5 squared is 25, times 0.1, 2.5, add 4, 6.5. And 6 squared is 36, times 0.1 is 3.6, add 4, 7.6. Now there are 7 times in this list, which divide the time interval from 0 to 6 into 6 subintervals. So the first subinterval, second, third, fourth, fifth, and 6th. So 7 numbers produce 6 subintervals. Those subintervals represented in our graph, 1, 2, 3, 4, 5, 6. A way to calculate the delta t would be to find the difference between the final time in our list, which we'll call b, and the first time in our list, which we'll call a, and divide that by n, where n is the number of subintervals. So in this case, that would be 6 minus 0, and we have 6 subintervals, confirming that delta t is just 1. Now plot this data on both of our curves, and then to calculate our lower estimate, I'm going to use what's called a left-hand sum using 6 subintervals, capital L sub 6. Meaning for each subinterval, I'm going to use the left value because that's the lower value. Be careful, do not assume that L implies lower. L implies left, and lower could be on the left or on the right, depending on the outputs of the velocity function. In our graph down here, for each subinterval, I'm going to use the left-hand side to find the velocity that I'm going to assume is constant for each time interval. And the left-hand sides will consistently give me lower estimates because of the increasing nature of our velocity curve. So visually, I'm going to find the following 6 areas. First time interval, assume 4 is a constant speed. Then assume 4.1, 4.4, 4.9, 5.6, and 6.5. The areas are easy to calculate because each delta t is 1 second. So the first area is 4 times 1, or 4. Then we have 4.1 times 1, 4.4 times 1, 4.9, 5.6, and 6.5. All of these are measured in feet. Now we're instructed to express each calculation in summation notation. Well, first of all, we know that the area of the first rectangle was found by plugging t sub 0 into the velocity function, and then we assumed that was the constant velocity, so we multiplied by delta t. The height of the second rectangle was v of t1, multiplied by delta t. Now all of my areas will have a delta t width, so I'm anticipating I can just factor them out. So I'll rewrite with delta t factored to the front. Third rectangle had a height of v of t2. Fourth rectangle had a height of v of t3. Fifth rectangle had a height of v of t4. And the last rectangle had a height of v of t5. Notice we never used this data here. Visually, this height here was never used as any of the heights of my rectangles. So the left-hand sum only uses this data. Now in summation notation, we can leave the delta t in front. We have a sigma to represent we're doing a sum. And we have v of t sub I. It's the I that changes from 0 to 5 from term to term. So we can say below the sigma that I starts at 0 and ends at 5. And in this case, delta t was 1, v of t0 was 4, v of t1, 4.1, and then the rest, stopping at a velocity of 6.5. Keep in mind our units, all of these numbers are velocities, and this 1 in front is time. So I'll have feet as my final unit, and we get 29.5 feet. And now we do an upper estimate. For each subinterval, it's the right side of the interval that is the higher velocity. So I will use what's called a right-hand sum, where we're using 6 regular subintervals. So for the two options in this first subinterval, we assume the right side is the constant speed, which is the greater one in this case. Right side is not always greater, depends on whether the velocity function is increasing or decreasing. But for this first subinterval, we're going to assume the 4.1 is the constant speed. For the second subinterval, we'll assume 4.4 is the constant speed. Third subinterval, we'll assume 4.9 is the constant speed, then 5.6, 6.5, and 7.6, giving me 6 rectangles. First area is 4.1, then 4.4, 4.9, 5.6, 6.5, and 7.6. And all of these measured in feet. Now is a good time to notice that these 5 areas that are on the right side of the left sum wind up being these 5 areas, which are the left 5 rectangles of the right sum, the reasons for which should be obvious. Again, every delta t is 1, so I can factor them all out. The first velocity we used was v of t1. That was the velocity at the right side of the first subinterval. And then v of t2, v of t3, v of t4, v of t5, and the last one we used was v of t6. In summation notation, we could leave the delta t factored out, and we can say sigma. We did v of t sub I, but this time I varied from 1 up to 6, meaning we use these times, and hence these velocities. So in this case, we had 1 times, and then these 6 numbers, which add to 33.1 feet. So we have a lower estimate and an upper estimate. It seems reasonable to average them to come up with a singular, better estimate. Now, as you can imagine, another way to improve accuracy is to simply use more subintervals. Here's a visual using technology. As we increase the number of subintervals, you can see that my left-hand sums improve in accuracy. Also true for my right-hand sums. They improve in accuracy if you simply use more and more subintervals. The bottom corner shows the left sum and the right sum and the exact area between the velocity function and the t-axis. Now in this case, our velocity function was increasing from left to right. If a function is increasing on an interval, then left sums underestimate and right sums overestimate the exact area. However, imagine a function that is decreasing on an interval. In such a case, the left sums would overestimate and the right sums would underestimate the exact area. Okay, let's go to the next page. We are continuing with scenario 1. Here once again is our velocity function that models the velocity of the runner. Because the function's rule is known, we can use many smaller subintervals to get better estimates for the total distance traveled in the first 6 seconds. Use summation notation to express both the left and right-hand sums, each for n equals 20, and then generally. This time I'll do this without a visual. So when n is 20, so we want to go from time 0 to time 6, and we want to break this into 20 subintervals. I won't show all of them, but the first one will be t sub 0, the last time will be t sub 20. Then we'll have t sub 1, t sub 2, etc., and the last few, working backwards, t19 and t18. The delta t, which is the width of each subinterval, can be calculated by doing the length of the entire interval, which is 6 minus 0, divided by the number of subintervals that we want. So in this case, we get 6 over 20, which is 3/10, or 0.3. Furthermore, we can calculate each t sub I by beginning with 0 and adding to it I delta t's, which in this case is just I times delta t. So t1 would be 1 times delta t, or it could be found by starting at 0 and adding delta t to it, and you'd get t1. t2 would be 2 times delta t, which you would get by starting at 0 and adding delta t twice to get to t2. This gives us the tools to say that L20 will be delta t times the sum from I equals 0 to 19 of v of t sub I. Now we know each ti is I delta t, so I can write this sum as delta t times the sum from I equals 0 to 19, v of I times delta t. Now for the rest, I'm going to use the calculator. I'm going to create a slider for n, type in n equals 20. I'll let it range from 1 to 100, step size 1. Let's type in our function, v of t equals 0.1 t squared plus 4. We want to calculate delta t, and it was equal to 6 minus 0, the width of the time interval, divided by the number of subintervals, which is n. And now I'll use capital L for my left-hand sum. This is equal to delta t times the summation sign. In Desmos, just type in sum for sum. I'll change the index to I and go from I equals 0 to, I want this to be n minus 1. Now for the summand, we do the velocity evaluated at I times delta t. We're getting an answer that has a decimal form. We can convert to fraction if we would like. And since this answer is exact, it's not a rounded decimal, I'll say equals 30.669, and this would be measured in feet. Now the right sum would be the exact same setup, except my i's will range from 1 to 20. So we have delta t times the sum from I equals 1 to 20, v of, and t sub I is I delta t. So in Desmos, I'll type in capital R for the right-hand sum equals delta t times the sum from I equals 1 up to n, and then v of I times delta t. And we get 31.749, and this is exact. Here's our fraction form, measured in feet. Now, generally speaking, delta t will be, if we go even more general and say that 0 and 6 are a and b, then delta t will be b minus a divided by the number of subintervals. T sub I will be begin with a and add I delta t, same structure as here when a was 0. The left-hand sum would be delta t times the sum from I equals 0 to n minus 1, v of ti, and ti would be a plus I delta t. And the right-hand sum would be the exact same, but I would start at 1 and end at n. So in our programming, I can now simply change n to different values, and this will automatically calculate for us the left and right-hand sums for the time intervals 0 to 6. Let's drop n to 3, and we confirm our answers we got on the first page of our notes, 28 and 35.2. Change n to 6, and we get the answers we got on the second page of our notes. And on this page, we had n equals 20, and we get these two values. And because the function is increasing, left-hand sums will produce underestimates. The table in our notes, when n is 20, the lower estimate, which was a left-hand sum, is 30.669, and the upper estimate, which is a right-hand sum, is 31.749 feet. Now I can simply change n to 50 and get my left and right sums, 30.985. I'll just round all of these to 3 decimals. And we have the upper estimate of 31.417. Change n to 100, and we get a lower estimate of about 31.092 and an upper estimate of about 31.308. As n gets larger, we get more and more accurate, and the estimations therefore get closer to each other as we increase n. If I change n to 1,000 and then 10,000, I start to see that the total distance gained in the first 6 seconds is about 31.2. Here's a program that shows the rectangles. I have it set up so that you enter the velocity function as f of x. You enter your left and right endpoints of the primary time interval, so from 0 to 6, and then you can specify the number of subintervals. You can show the left rectangles, show the right rectangles, and you can toggle on or off these vertical lines. When n is large, it's better to leave these invisible. I'll leave the right-hand rectangles showing, and as n increases, you can see our approximations improving. Over here, we see the left and the right getting closer and closer to 31.2, which is the exact area. These sums are 2 examples, or 2 types, of what are called Riemann sums. Generally speaking, a Riemann sum is a sum of the areas of a multitude of skinny rectangles that approximates areas between a function and the horizontal input axis. There are other kinds of sums, such as midpoint sums, that can also be used to approximate areas between a function and the horizontal input axis. Okay, next page. Now, as the number of subintervals n approaches infinity, the approximations for the area or areas between a curve and the input axis using either left or right-hand sums approach an exact value. Finding this exact value is called integration and is represented by a definite integral as shown below. Okay, here are 2 general expressions for left and right-hand sums. We're just using a general function f instead of a velocity function. We're using x sub I instead of t sub I, and we have a delta x instead of a delta t. Here we're going from I equals 0 to n minus 1. This is an indication that this is a left-hand sum, which I'll write as LH sum. The second one starts at I equals 1 and ends at n. This is the range of i's we would use for a right-hand sum. Now, as n approaches infinity, so we do more and more rectangles, both of these will approach an exact value, which we represent with a new notation that mirrors these summations. Instead of using a sigma for a sum, we use an elongated s. Instead of putting the starting and ending values of the index of summation, we put the values of a and b, which are the left and right endpoints of the interval over which we want x to vary ultimately. Now this part of the summand is replaced with just saying f of x. And then the delta x is written after the f of x, and we use a differential dx. This entire expression is called a definite integral. The b, which is the right side of this interval, is also called the upper limit of integration, and the a is the lower limit of integration. This elongated s is called an integral sign. The function there is known as the integrand, and this dx is called the differential of x. All of these components must be present to be a definite integral. Technically, the operation between the integrand and differential is multiplication, although sometimes this dot is left off. Now for each case below, the magnitude of area of each region is given. Give the value of the definite integral of the function over the interval from a to b, accompanied by appropriate units. In this first case, let's say that the magnitude of the area is 18, referring to this region right here. And the word magnitude simply implies give a positive value no matter what. Like the magnitude of 5 is 5, and the magnitude of -6 is 6. When you do a definite integral of a function over an interval where that function is above the horizontal axis, then when you do your Riemann sum, all of your outputs are going to be positive, meaning that all of these calculations will be positive. Delta x will be positive in both cases, so you'll get positive answers. So in this case, the definite integral from a to b of this function, f of x, dx, would be equal to this 18. And the unit would be, just like you're doing length times width, would be the unit of the input variable multiplied by the unit of the output variable. So in this case, it would be meters times meters, or you would get square meters. And in this case, this 18 actually represents area in the traditional sense of two-dimensional space. So an area that is an area. Now in this next case, when a function is below the horizontal axis, in this case a u-axis, then all of the outputs of the function will be negative, meaning that all these numbers in your Riemann sums will be negative. The dx's will be positive, but your overall sums will be negative. Now we're saying that the magnitude of this area is 11, referring to this region. So our integral from a to b of this function, which is g of u, the differential will be du this time, will be equal to -11 because the function is below the horizontal axis. And then the unit will be the unit of the independent variable times the unit of the dependent variable. So when you do dollars per pound times pounds, you get dollars. This parallels the velocity scenario where the change in monetary value was a decrease by $11. More on that in the next lecture. In our third case, we have a function h of t that is partly above and partly below the horizontal axis. In this case, a t-axis. The magnitude of this area is 7, and the magnitude of this area is 3. When you do a definite integral from a all the way to b, so from here all the way to here, of this function h of t, differential dt, we will get positive values for any areas that are above, so 7, and then add to that a negative area for any regions below. So we have some offsetting occurring, or cancellation of areas. And in this case, we get a 4 as the result. The unit on this 4 will be gallons per second times seconds, which gives us just gallons. This parallels the runner situation. For the first bit of time, some amount gained 7 gallons, but in the second interval of time, we lost 3 gallons. So overall, our net change was 4 gallons. We'll discuss this idea a little bit more in the next lesson. Okay, let's go to the next page. Scenario 2. Okay, so we have a new scenario to think about. Again, this will involve velocity. A car is initially 1 mile to the right of a house. The velocity in miles per minute as a function of the number of minutes is v of t equals -0.1 t squared plus 1.6, whose graph is below for t between 0 and 6. If v is positive, then the car is moving right. If v is negative, then the car is moving left. Do the following. Use technology to approximate the distances traveled by the car in either direction. All right, keep in mind that the graph here is a velocity graph, not a position graph. So you have v against t. This portion of the velocity graph is above the t-axis, so positive, thus the car is moving right. This portion is below the t-axis, so the velocities are negative and the car is moving left. I'm going to include a schematic to show where the car is at different times. So we have a house along a linear path. The car is initially 1 mile to the right of the house. So at time 0, the car is here. Now we're going to say that the house is our frame of reference. So this is position 0. At time 0, our position is 1, meaning 1 mile to the right of the house. Now use technology to approximate the distances traveled by the car in either direction. So this area, where the velocity is positive, will correspond to increases in position of the car, meaning the car will go further to the right. So we're interested in going from 0 to 4 minutes. Now, if I didn't have the visual, I could find when the car is at rest by solving 0 equals v of t. In other words, 0 equals negative 0.1 t squared plus 1.6. Add the 0.1 t squared to the other side. Divide by 0.1. We get t squared is 16, so t is plus or minus 4. And in this context, we're only concerned between 0 and 6, so I only care about the 4. The car will be at rest at this time. Furthermore, I know that the car will be further to the right. So in my schematic, I can already predict that at time 4 will be somewhere further to the right. Now, to aid me with technology, I'll use this program. For v of t, I'll enter f of x equals, and then use x instead of t. I want to do approximation from 0 to 4, and I'll begin with 10, and I'll show my left-hand sums. Let me change my scale to see this better, and keep track of these values. Let's just go to n equals 100. So in my notes, I'll combine steps 1 and 2 into a table. So when we're moving right, that's the time interval from 0 to 4. L100, the left-hand sum using 100 subintervals, gives me about 4.299 measured in miles. R100 gives me about 4.235. Notice L is greater than R. That's because we have a decreasing function this time. The left-hand sums are overestimates. Now the exact can be represented by a definite integral. From 0 to 4, we put our velocity function and then dt. And we're going to use technology to help us with this. Here's a blank sheet of Desmos. To create a definite integral, type in int. 0 is the lower limit, 4 is the upper limit. We'll put our v function in parentheses here. It was negative 0.1 t squared plus 1.6. And then outside the parentheses here, put your differential. If you're using t's as the independent variable, then make sure you put dt here. Then we have this decimal or this exact fraction. Our exact answer is 64/15, which when we round to the same number of decimals is 4.267 measured in miles. I'll use decimals in my schematic here. Between time 0 and time 4, the car moved right 4.267 miles, putting us at a position of 5.267 miles right of the house. Okay, now let's figure out how far the car moves left between times 4 and 6. Back to this tool, change A to 4 and B to 6. I'll keep 100 rectangles and bring this into view. We can see our left sum using 100 rectangles is approximately negative 1.847 miles. Our right sum using 100 rectangles was about negative 1.887 miles. You can see my program showing the exact area, which you can also find by typing in this definite integral, but doing integration from 4 to 6, and in fraction form is negative 28/15, which is about negative 1.867 measured in miles. So between time equals 4 and time equals 6, we'll have headed back towards the house, having gone left 1.867. That would take us to a new position of 3.4. So at the 6-minute mark, the car is 3.4 miles to the right of the house. Question 3 says, use technology to find the exact change in position from 0 to 6 minutes. So I go back to this integral and I change my lower limit from 0 and my upper limit to 6, and we get 2.4. So the integral from 0 to 6 equals 2.4 miles. This change in position says that in the first 6 minutes, the car should be 2.4 miles to the right of its initial position. The car started 1 mile to the right of the house. It's now 2.4 miles further to the right. So this 2.4 is a change in position, putting us at a new position of 3.4. And then predict the position of the car relative to the house at the 6-minute mark. Well, we've kept track of that as we've gone. So we would say that S of 6 minutes, meaning what is the position at the 6-minute mark, will be 3.4 miles, meaning that we are right of the house. A negative value of S, which is possible, would mean we're to the left of the house. Perhaps at a later time, that would be the case. Note that the definite integral of velocity gives the change in position over the interval. In other words, when you do a definite integral from A to B of a velocity function, you get a change in position represented by the position at time b minus the position at time a. So we integrate from 0 to 6, we get this change in position, meaning the position at time 6, which is 3.4, minus the position at time 0, which is 1, gives you the 2.4, which is the change in position. In the next lesson, we will explore this relationship a little bit more and then generalize it. But for now, we conclude this introduction lesson on integration.